In this video, we want to take a look at inverse matrices. That is, we want to find matrices that behave like reciprocals. Right? Remember that if you have any real number and you multiply it by the reciprocal of itself, then you end up with the multiplicative identity 1, right? For instance, if you take 3/5 and you multiply it by 5/3, you get 1. These two numbers, 3/5 and 5/3, are multiplicative inverses of each other. And why am I writing so small here? Let's make this a little bigger. So we've got that notion for real numbers. Let's do a similar thing for matrices. Now I'm going to put some definitions down here, and the book sort of jumbles them all up. I got the book showing over here, definition 1. There's actually 3 definitions in here. So there's, yeah. So here we go. Definition. We say, given an n by n matrix, let's just write it this way. If A is an n by n matrix, we say that, I don't want to go over there. We say that A is invertible if there exists a matrix B such that A times B equals B times A. It's not seeming to keep up with me here. B times A equals an identity matrix. And it'll be an n by n identity matrix. So we say that A is invertible if there exists a matrix for which this happens, okay? In the event that it happens, so this was, I guess, my first definition here. I've got another definition. In the event that this happens, B is called an inverse of A. And 3, if you can't find it, A is called singular. If no matrix B exists. If there is no such matrix that this works, then we say A is singular. Okay. We should point out that a matrix doesn't have more than one inverse. If it has one, it has only one. So let's scroll up a little bit here, and this is actually a theorem. It says, if B and C are both inverses of A, then they're equal to each other. Let's slide back over here. Then B equals C. And the proof of this is actually pretty straightforward, pretty easy. So let's do it here. Proof. So what I'm going to do is I'm going to point out here that since I know that B is an inverse of A, we know that B times A is equal to an identity matrix. Likewise, we know that A times C is equal to an identity matrix because they're both inverses of A. what I wanted to do is show that B actually equals C. Okay? So let's just start off here with C. And I want to note that C is equal to I times C, where I is an identity matrix. Right? This is like multiplying by 1. If you take any matrix and multiply it by an identity of the appropriate size, then you get the same matrix back again. But I have from right up here that that identity matrix can be written as B times A. So I'm going to write this thing here as B times A times C. Then I'm going to use a property of matrix multiplication that it's associative. So I keep the order the same. It's still B, A, and C, but I'll multiply these two together first and then that one. I cannot commute, right? Multiplication cannot be switched order. But I'm not switching the order, I'm just switching the grouping, and that is okay. However, now I'm looking at this saying, hey, A times C, that's the identity matrix because C is an inverse of A. So this is B times an identity. But an identity matrix times any matrix is the one that you started with there. So that's equal to B. And what I end up with here is that C is equal to B. So if you got two inverses, you really don't have two inverses. You have only one. So there's only one inverse at most for a matrix. Right? And here's some notation here. The inverse of A is denoted this way. We use a -1 exponent, just like we would use a -1 exponent to denote a reciprocal for real numbers, right? This is just like if you had 4 to the -1 power, you literally mean 1 over 4, right? Now, we don't really divide by matrices. We multiply by the multiplicative inverse here. Just as we could say, we don't ever divide by numbers. I never divide by 4, I just multiply by 1/4. You know, we think of it as division, but we can coax it in terms of multiplication. And that's what we do in matrices. We multiply by inverses. Okay. Now, we're going to spend some time in later sections calculating inverses in different ways. I want to just end this section with, or at least this video, with 2x2 inverses, because it turns out these are pretty easy. So it goes like this. If A is equal to just your standard 2x2, so A, B, C, D, then A inverse is, there's a scalar I'm going to multiply out in front, so 1 over AD minus BC times this matrix, and this matrix is, I'm going to swap the main diagonal here, so the D comes up here and the A goes down there. The B and the C stay in the same place, but we'll make negative signs in front of them. Okay. This is, of course, provided that you're not dividing by 0. And as long as you're not dividing by 0, then A is invertible, and this is what it is. In fact, for 2x2 matrices, it's going to turn out that this is really all you need. Not every matrix has a determinant. But for 2x2s, you can just say, well, multiply the numbers together on the diagonal here, and then multiply them on the off diagonal, and subtract them. So AD minus BC. If that number is 0, then you can't do this calculation, and you don't get an inverse. If you can do this calculation, I mean, if this is not 0, then you can do this calculation, and you do have an inverse. Okay? So, for instance, I can do, oops, come on now. For instance, if I say that A is the matrix, how about something like 3, 7, 1, 3. I notice that AD minus BC here is 9 minus 7, which is 2. So that tells me that the inverse A inverse then is going to be 1/2 times, the 3's will swap places. It's kind of hard to tell that I actually swap places, but anyway, the 3 and the 3 turn around. If I can get that to look like a 3, there we go. And the 7 and the 1 stay where they are, but we'll throw a minus sign in front of them. So distributing the half in here, I've got 3/2, -7/2, -1/2, and 3/2. And I want to just quickly check that this is indeed an inverse to the matrix that I started with. I do have time left on this video, so let's scroll up a little bit, put this right here, and let's just check it. If I take my original matrix here, 3, 3, 1, and 7, weird stuff is going on, and I multiply it by what I think the inverse is here, 3/2, it's a -1/2 right there. That's actually 7/2, and 3/2. So let's try it. I've got, this would be 9/2 -7/2. And then I've got 3/2 -3/2. And I've got 21/2. Oops. This was supposed to have a minus sign, wasn't it? There was a minus sign there, and I lost it there, so there's a minus sign right here. So -21/2 plus 21/2. And lastly, I've got -7/2 plus 9/2 for a grand total of, well, this would be 2/2, but that's 1. This is a 0. This is a 0. And this is a positive 2/2, but that's 1. So there we go. Multiply those two numbers together. I got an identity. This is the inverse of that. Now for bigger matrices, 3x3, 4x4, it's going to be a little more work to come up with the inverse matrices. But for 2x2s, it's pretty simple. Swap the entries on the main diagonal, make the off diagonal negative, and then multiply by 1 over AD minus BC. Okay, so there you go. There's your introduction to inverse matrices.